Hello everyone and welcome back to another video. Today we're going to be covering a couple of mathematical topics, specifically Ceva's theorem, and then we're going to be doing that with mass point geometry, which makes this applicable to our physics channel. And we're going to be doing a AMC 8 problem that requires or that can use mass point geometry. And the reason we're doing this is because, of course, mass point geometry is almost entirely just physics. So let me go ahead and first explain Ceva's theorem, which is what we're going to be proving today. And it states that if you have some triangle ABC and you have some concurrent Cevians AX, BY, and CZ concurrent there, then Ceva's theorem tells us that ZA over BZ times XB over CX times YC over AY is equal to 1. And these lengths can be directed as well, but today we're just going to be focusing on the undirected version. And it tells us that this is actually an if and only if statement. So if ZA over BZ times XB over CX times YC over AY is equal to 1 if and only if AX, BY, CZ are concurrent Cevians. And so we're going to be proving this by placing some masses here, here, and here, and forcing the ratios to come out like that. Okay, so let's get to the proof. So let's consider a triangle again. And we're going to consider a triangle with mass MA here, mass MB here, and mass MC here. And they're all going to be connected by some massless rods. And let's say the center of mass is somewhere like here. And we're going to consider the concurrent Cevians through this center of mass. So right here. So we're going to consider these three concurrent Cevians. And you might say, well, this point is fixed, so we're not really saying anything, but this point can be moved around anywhere by adjusting these masses, since these masses are just constructs that we have created. So from here, there's two arguments that we can do here to finish off the proof. So the first way is to say that the center of mass of these two lies right here. And the reasoning we have for that is that when you have like three particles, then let's say we have three particles here, then the center of mass of all three particles can first be finding the center of mass of this one and that one. And let's say the center of mass is here, and we replace it with, let's say that's M1 and M2, and we replace it with some equivalent with M1 plus M2 at the center of mass of these two. And then all of this is just equivalent to this, so the center of mass of the entire system lies somewhere on this line. So then that means the center of mass of these two must lie on the line MC through the center of mass. And so then we can say that the ratio, if we name these points again, A, B, C, X, Y, Z, then we have that MB times BZ is equal to MA times AZ, since that's how you find the center of mass. But the other argument, but this seems a little bit backwards to me. So the other way to argue this is this is going to be a 3D picture. Let's place this triangle on some ledge. And this ledge will go through point C in this case, and points A and B will be here, with the two masses. And then and this point here is Z. And if CZ goes through the center of mass, that means this whole thing is balanced because there's no net torque, since the gravitational force on the center of mass acts here. And so now we can balance torques individually for all 3 points. And there's going to be no force here because a normal force is going to cancel out the gravitational force, and that means purely MA times AZG is equal to MB times BZG is the only condition we need. And both of these have found the same thing. MB over MA is equal to AZ over BZ. And we can just repeat this argument for all 3 points, right? So then MC over MB is equal to BX over XC. And lastly, MA over MC, I can refer back to here, MA over MC is going to be equal to YC over AC. And look at that. If we multiply all 3 of these equations together, then we're going to have MB over MA times MC over MB times MA over MC, and all these cancel, so this is equal to 1 is equal to AZ over BZ times BX over XC times YC over AC is equal to 1. And we have proven the only if direction, we have proven the if direction of Ceva's theorem. And we've done that purely with physics. No math here was actually done except for this part of writing out the equations. So now we just need to prove the direction that if these three are equal to 1, then the Cevians are concurrent. And this can be done with a phantom point argument. So that is, if we have a triangle with the given conditions, then we have to prove that these 3 are concurrent. And we can do that by saying that if this is in fact true, then let's consider the intersection of AX and BZ, which I'll denote with AX cap BY. Then this intersection here, we can consider, so let's suppose these CZ is actually not concurrent, and CZ is something like that. And let's call that Z prime and make it intersect with C. Then we in fact have that AZ prime over BZ prime times BX over XC times YC over AC is equal to 1 by the forwards direction that we have proved. But then AZ over BZ times ditto is equal to 1 as well. So then we clearly see that Z and Z prime have to be the same points. And this was just purely a logic. So I guess we're still not doing math here. So now that we have proven those, let's move on to the AMC 8 problem. And this is basically going to be using the same ideas of placing masses so that we can find what we want. So here's the problem here. This is problem 24 from the 2019 AMC 8. And it states, in triangle ABC, point D divides side AC so that AD to DC is equal to 1 to 2. Let E be the point of BD and F be the point of intersection of line BC and line AE. Given that area of triangle ABC is equal to 360, what is the area of EBF? Let me make that a little bit larger. And the way we're going to solve this problem is by placing masses at these points and letting the center of mass of these two be this one, letting the center of mass of these two be this one, and ultimately letting the intersection of the two be the entire center of mass. And we can do that to find the ratios. So we first have AD to DC. AD to DC is equal to 1 to 2. And we're making this be the ultimate center of mass. And we derived earlier that means if we have MC and MA, we have MA over MC is equal to CD over AD. So, and as evident in the picture, that means MA is equal to 2 times, since this is 2 to 1, MA is equal to 2 times MC. So let's just give it a mass of 2 and give this a mass of 1. So then the next thing we have that is, so we can place an equivalent mass of 3 at D, and then we know that these two are going to be balanced since this is still the center of mass. And by considering the equivalent mass of 3, then the mass here also has to be 3. So then voila, we have 3 to 1 is equal to CF to BF by that thing we proved earlier. So then CF to BF is equal to 3 to 1. So then all we have to do here is, well, we have to find EF to AE, which is actually preferable. And so since this is 3 and 1, the equivalent mass we place here is 4, and the ratio between CF to sorry, what point is this? FE to AF, AE, FE to AE is equal to 1 to 2. So then the triangle of, so now this is just math. So the area of triangle BEF, which I'll denote with brackets, is equal to 1/3 the area of triangle ABF. Since the height is the same with this entire triangle and this smaller triangle, and the only difference is the length of the bases. And now the ratio between the area of this triangle and the entire triangle is, well, CF to BF is 3 to 1, so BF is 1/4 of BC. So BEF is equal to 1/4 times 1/3 times the area of triangle ABC. And so the area of triangle BEF is 360 times 1/12, and so that gives us 30. And so this is a bit of a fun video, and that's going to be it. So we proved Ceva's theorem here by placing masses here and letting the concurrent Chevians go through the center of mass. And then we also solved this neat little AMC problem using mass points, and we didn't even have to construct any parallel lines, which would be probably the more classical approach to this problem. I hope you enjoyed the video. If you have any questions, leave them down in the comments below, and please subscribe. Thanks for watching.